actually prove the fundamental theorem of calculus. So we've been using this for a while now, but I want to go through the proof. Before we do that, let's just review a little bit about what it says. So I'm pulling up the 5.3 notes. You've written down most of this, but eventually I'll take us to the page where we do the proof. But I just want to put this up one more time. So how does this, what's the idea here? Well, we've got some function f. Okay? We could write f of x. There's nothing wrong with writing f of x, but we just don't, we want to make sure we don't get this x right here confused with this x up here in the area function. Okay? So then we define a function, and I'm not showing you the graph of the function right now. What I'm showing you is how you would compute the output values for the function. Okay? So for example, if this area were 5, then what would g of, and here x, maybe when x is 3, what would g of 3 be? G of 3 would be 5. That's what I'm saying. That when you plug in a 3 for x, it outputs an area underneath the curve of 5. So this is this area function that we've been working with. Okay? So this is this g of x, which is this area function. Again, when you're having trouble, because there's a lot of symbols in that function, okay, when you're having trouble looking at it, first identify the variable. The variable is x, the upper limit of integration. So the way I think about this function is I think about taking that x point right there and sliding it back and forth. And as I slide that x value back and forth, the output is the area underneath the function, and that will be changing. So now here's the question, and this is the fundamental theorem of calculus. How does the area change as I slide x back and forth? It changes based upon what?
The shape of the graph.
The shape of the graph of f. Exactly. It changes based on the shape of f. So if I were to slide x, let's see if I can even do. I might even be able to do this. Let's see if I can. No. Let's see here. Yeah, that'll work. If I. Oh, no. So now if I take and I slide x. There we go. As I slide x, what's going to happen? The area is going to increase in this case. But how much does it increase by? Well, it depends on what the shape of f of x is doing. Right? So as I slide that x back and forth, okay, we're going to be adding or subtracting area, and that's going to be based on the shape of what? The function that we're finding the area underneath. Okay? So that's what the fundamental theorem of calculus says. So it says, given our area function right here, okay, then this function is continuous and differentiable. Okay, those two parts are sort of important, but not the most important part here. Okay? The most important part is, well, once we've said it's differentiable, what is its derivative? How does, so remember, when we say what's its derivative, that's saying how does it change? How does g of x change? It changes by f of x. Okay? So that's the fundamental theorem. Okay? Of course, I could write it another way. A more compact way is just to say, take the derivative of this expression. And what is its derivative? It is just f of x. Okay? This one here, the one I just wrote, is especially intimidating to students to look at. Okay? But it is just saying, here's our area function. We said here's our area function. What's the derivative of the area function? What's its derivative? It's f of x. So what's the derivative of the area function? All right, we've listed it there as f of x. Okay, so I now want to go ways down into this document. Oh, I think we're on page 5 here. And let's prove the fundamental theorem of calculus. So that was a quick review of it, right? I mean, our goal is to show, we want to show that for g of x equal to a to x of f of t dt, what do we want to show? We want to show that g prime of x is equal to f of x. Well, what is g prime of x? Let's return all the way to the first unit, maybe the second unit of this course. Recall that g prime of x, or the derivative of any function, is what? It's the limit as h approaches 0 of the difference quotient. Right? So we're going to have to return all the way back to the difference quotient. Okay. So this is our goal. We need to do this to do the proof of the fundamental theorem. Okay. Before we do that, I want to say at least one other thing. I want to kind of prime us for this. Okay. So the next thing I want to say is let's just consider some random function here. Let's call it k of x. And k of x, let's say, is defined on the interval from x to x plus h for a given h. For a given h. So pick an h value. It doesn't actually have to be positive, but if it's not positive, then I have to turn my picture around. But let's go ahead and just assume h is positive, but it doesn't have to be. If h were negative, then it would just go x plus h comma x. You would just invert this interval, right? But I need to have a direction here, so let's just do that. Okay, so consider k of x on this interval. Okay, then let's let x of h star be just some random point in that interval. Don't let your eyes glaze over with that notation. The star we usually use a star when it's just some random point inside of an interval. We usually put a star on it. The subscript h that I'm putting there is because I'm going to vary h. So as h changes, my choice of xh star will change. Okay. So here's my question to you. What is the limit as h goes to 0 of k of x h star? Because we're going to need this idea at the very end of our proof. So I want to get the idea out of the way first so you're comfortable with it. What do I see here? Well, I see that this piece right here, so this is my left endpoint of the interval, and it's fixed for some given x. And this is changing with h. As h goes to 0, what happens to this interval? The left side stays put, but the right side starts shrinking towards the left side, right? Do you see that? I feel like you'd start out with an interval like this, and this is going to stay put, but this is going to move in as h goes to 0, right? So as that happens, as h goes to 0, x of h star gets closer and closer to what?
X.
Yeah. If it's trapped, go to your Star Wars metaphor, if it's trapped in the trash compactor and the one wall of the trash compactor's closing in on it, where are you going to end up at? At the one wall, right? Same idea. As this endpoint gets closer and closer to here, my xh star, which is always between them, is going to just go to x. So that means that this limit right here, oops, is just going to be k of x. This is, of course, assuming, and I should have said this, for k a continuous function. This only works if the function is continuous, or it's only guaranteed to work if the function is continuous. Does that part make sense? Because that's going to show up at the very end of our proof, and I'm going to say, therefore, we're done. Okay, I'll revisit this, but I mean that's what's going to happen at the end of our proof. We're going to need some argument like that. Okay. The next thing I want to do, I have one more thing to remind you of before we actually do the proof. We had this idea right here. If I have a function on a, b, and maybe here's my function, and it behaves, I don't know, maybe something like that, then this function has a max on this interval. Where is it? Maybe right here. Capital M. And it has a minimum on this interval. Maybe right here. Lowercase m. Okay. And we gave a nifty little theorem about a week and a half back, where we said, well, little m times b minus a is going to be less than or equal to the area underneath the curve, which is going to be less than or equal to capital M times b minus a. Do you remember that theorem? Or that property? We went through that one about a week and a half ago. What's the picture, or what's the idea? I mean, we've got a lot of symbols up there. What are we thinking of for this property? What type of objects are we dealing with? How about this? What's that?
A rectangle.
Rectangles, right? What is this right here? This is this rectangle. Let me shade this rectangle here. I'm going to erase it once I do it, but let me shade it for you. That's the area of that rectangle, right? It's got a height of what? It's got a height of m, and it's got a base of b minus a. So this right here is that black rectangle. Okay. I'll let you decide whether if you can fit that in there or not. I'm going to erase it just because now I want to do the same thing up here. What is this?
That's the area of the upper.
Yeah, that's this area right here, the area of that rectangle. And what do we know about the area underneath our curve? It's got to be somewhere in between the two, right? The smallest it could be is the area of the small rectangle. The biggest it could be is the area of the big rectangle. And it's essentially trapped in between the two of them. Okay? So don't forget that property, because that's we need that. All right, so here we go. Oh, already down to the end of the page. Here we go. Here's the proof of the fundamental theorem. Okay? So we're going to start out with our difference quotient without the limit. I'll put the limit in here in a little bit. Let's look at g of x plus h minus g of x all over h. Okay? The first thing I'd like to do is let's go ahead and just rewrite this slightly. Let's write it as 1 over h times g of x plus h minus g of x. Everyone see what I did there? I just pulled out the 1 over h in front. Okay, but what was g of x? I hope you know this function. I hope you know this function. You've been working with them for 2 weeks now. I hope you know this function. This is the function that goes from a to x plus h of f of t dt. That is g of x plus h. What did I do? I took g of x. I took g of x, and everywhere I saw an x, I plugged in an x plus h. Minus just the regular g of x, minus the integral from a to x of f of t dt. Any questions on that? All right. So this is equal to 1 over h times, and now I'm going to do something a little sneaky. Okay, you've seen me do this a couple times. I'm going to rewrite this as the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt. That all is this underlying portion right there, and then I still subtract off the integral from a to x of f of t dt. And one way to look at that is if I had this picture right here, here's my f of t, and it doesn't have to, the picture doesn't have to work out this way, but it's easier to draw if it does. If I want to go from a to x plus h, what could I do? If I want to find the area underneath the curve from a to x plus h, I could stop off at x. right? And I could find this area first. That would be the area from a to x, and then add to it the area from x to x plus h. Add up from a to x, and then from x to x plus h. Well, that's kind of nice, because now one of those terms sort of cancels. I don't know if we made the problem easier or not, but now we're down to 1 over h times the integral from x to x plus h of f of t dt. Okay, folks, is this the derivative? What do we start off with? We start off with this guy right here. Is this the derivative? Is this how we calculate the derivative?
Yeah.
It's the difference quotient. The derivative has a difference quotient in it, but is this a derivative? Everyone say no, it doesn't have limits. All together.
No, it doesn't have limits.
No, it doesn't have limits. Can you have a derivative without a limit?
No.
Not necessarily. So what I need to, I can always calculate this difference quotient, but what do I need? I need h to go to 0 for this to actually be the derivative, right? So I haven't taken the limit yet. Okay? So we want to find all that remains. So all that remains is to find the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. Folks, I had a bad day the other day. My head wasn't working. I was working through this proof again. I've done this proof about a dozen times. Working through it again. And I actually had an idea. It was really nice, and it kind of cleared up my head. I've said that all of calculus is built on these indeterminate forms. All the big ideas in calculus are built on indeterminate forms. Is this an indeterminate form? How come? Sure, we have something divided by 0. That's not an indeterminate form, right? 3 over 0 is not an indeterminate form. It's just flat out undefined. So that's not indeterminate. What is an indeterminate form that's kind of like that? 0 over 0 is an indeterminate form. Is this an indeterminate form, 0 over 0?
No.
Is it? This was my idea. Kind of excited about it. Sharing it with you. If I did direct substitution here, I'd have a 0 here in the denominator, which you can't do, right? I'm just looking at the form. I'm looking at the structure. I have a 0 in the denominator, and I put a 0 up here. That would leave me with the integral from what to what? X to x. What is the area underneath the curve from x to x? 0. So this whole quantity is tending toward, this whole quantity right here is tending towards 0. As is the thing I'm dividing it by. I know I didn't put the divided by down here because it's a little strange to put an integral in a numerator of a fraction. But this is still an indeterminate form, 0 over 0. It's still an indeterminate form, so that we didn't get away from them. Since day one, we've been dealing with indeterminate forms. Okay, so all that remains is to take this limit, but whew, good luck. I don't know how to take that limit. Okay. So what are we going to do? We're going to play catch the cat. What do? You got a cat running around that you're trying to catch, so you start boxing it in, boxing it in, boxing it in. Okay? What do we know about the area underneath any curve? Well, we know that it's less than the area of its minimum rectangle that it could be fit into, and greater than the area of its minimum rectangle, and less than the maximum. Thank you. So what do we know? We know that this area right here, from x to x plus h, the area in this curve, now notice I don't have the over h yet. We know that this is less than the minimum times h, which is less than or equal to the maximum times h. Why did I put h as the width of that? because what's the width of this interval? It goes from x, let's do a different color. It goes from x to x plus h. How wide is that? It's h wide. So this is the base of the entire region. And so that's that minimum rectangle. That's that maximum rectangle. Going back to this picture right here. It's the exact same property. It's just being applied here. I've got x and x plus h, but it's the same idea. Okay. Now, we have one condition on f. What is it? What is the one condition we impose on f? That it be what?
Continuous.
It be continuous. We've got a closed bounded interval. We've got a maximum. We've got a minimum. We need to guarantee that f actually achieves its maximum and minimum. By the extreme value theorem, since f is continuous, there exists a u and v. Those are two separate things. Let me say it like this. There exists, let's say it like this, a u contained in x to x plus h, and a v contained in x to x plus h, so that f of u equals little m, and f of v equals capital M. Why does this work? Since f is continuous. So the extreme value theorem says any function on a closed bounded interval will actually arrive at its maximum and minimum. There's some input values that guarantee you'll get output the maximum or minimum. Okay? So if you look at this picture here, what I'm saying is I would call this my u. Why? Because what's f of u? The minimum. And I would call this my v. Sorry, let me not put it up there. I would call this my v, right? Because this is the order pair v comma f of v, and what is it equal to? The maximum of the function. How do I know I can do that without even knowing what this function is? Because I do know it's continuous. All right. So, returning to that, this statement right here, this line. Okay. So I can rewrite this line as f of u times h is less than or equal to the integral from x to x plus h of f of t dt, which is less than or equal to f of v times h. So all I did was replace the maximum and minimums with the actual output values in the function. So close, folks. I'd now like to divide all three sides of this by h. Here I need to make an assumption. H does not equal 0. And let's assume, without loss of generality, without loss of generality, assume h is positive. Okay. This proof works just fine. It works the exact same way. If you assume h is negative, you just have an extra step. But you have to pick one, because I'd now like to divide this inequality by h. And whenever you divide an inequality, the resulting signs on the inequality, that depends on the sign of the number you divided by. So I want to go ahead and just assume that it's positive. H is positive. So when I do so, I get f of u is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to f of v. So the minimum value is less than this quantity, which is less than the maximum of the function. Okay, does everyone see what I did here? I just divided this h into each term. Okay? How come I knew I could leave the direction of the inequalities the same? Because I assumed that h was positive. Now, if h were negative, what would I have to do? I'd have to change the direction of this sign, I'd have to change the direction of this sign, but what else could I do? Well, this is the smaller quantity up here, and this is the larger quantity, so I would then invert it. So I would invert these two, give myself another negative, divide that other negative through, and I would eventually get back to this expression that we have. So it doesn't matter whether it's positive or negative, It's just if it's negative, you have one extra step to do. Yeah? Okay. What have I just done? We got the cat trapped, right? We're trying to get a limit on this guy right here, right? That's all that remained, is to take the limit as h goes to 0, but I couldn't do that limit. But now I've got a function on its left and a function on its right. What am I hoping to apply here?
The average.
No?
The square
Good guess? What's that?
The square theorem?
Yeah, the squeeze theorem, the sandwich theorem. Yeah, you can call it whatever you want. The sandwich theorem, the squeeze theorem. I would now like to, now that I've got this function trapped in between these two functions, let's look at the limit as h goes to 0 for this one, and the limit as h goes to 0 for this one. So taking the limit of all three sides, we get the limit as h approaches 0 of f of u is less than or equal to the limit as h approaches 0 of 1 over h integral x to x plus h of f of t dt, which is less than or equal to the limit as h approaches 0 of f of v. I claim that this limit right here on the left-hand side, I claim that this limit right here is just f of x. How come? Well, where was u? U was a number inside this interval, right? Where was u? U was this number right here that was sitting inside this interval. As h goes to 0, what does u go to? X. So as we said, one thing I said, hey, don't forget, we're going to keep this idea. Here it is. That's what's showing up right there. I've got a number u. Where'd it go? Where'd it go? Oof. I've got a number u that's trapped inside this interval. The interval is collapsing down to just the point x. So if I take f of u, when I look at the limit as h goes to 0, it becomes just f of x. Now I can only do that because of y. What did I say way up here when I showed you this? This only applied for what type of function? Continuous function. Which is, so we need continuity twice in this proof. We need it once for the extreme value theorem, and we need it once to be able to collapse a function onto itself like that. So this gives us this is less than or equal to the limit as h approaches 0 of 1 over h of x to x plus h of f of t dt. But what does this limit go to? It goes to f of x also. We caught the cat. It's trapped. It's got nowhere to go. What is this whole big expression right here in the middle? That was our difference quotient. Therefore, g prime of x, which is this guy right here, equals what?
F of x.
F of x. There's some smiles in the classroom. I'm trying to hide it. It's okay. That is the fundamental theorem of calculus part 1. It required us to use basically all the tools we've been developing the entire semester. Right? At the beginning of the semester, we introduced limits. Then we talked about continuity. Then we introduced derivatives. Limit definition of derivatives. We talked about indeterminate forms. We then introduced the extreme value theorem. We then played some games. We learned how to take some new derivatives, right? We learned how to take harder and harder derivatives, second derivatives, graphs and things, applications. Then we returned to this new idea of the definite integral, which is an area function. And we just learned that the derivative of an area function is the shape of the underlying function. Da, 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 da. All right. That was the proof. Go ahead and draw yourself a little box and shade it in. Ah. So pat on the back. Okay. So many people missing today. You decide if you want to share this information with them. I'd keep it to yourselves. It's a fundamental theorem. Not everyone needs to see it. All right. All right, fundamental theorem of calculus part 2 is the practical one. Part 1 is the heavy lifting, part 2 is the practical application. Okay? Who cares that we can take the derivative of the area function? Well, I do, but maybe you don't. Okay? But once we can do that, we can now prove the fundamental theorem of calculus part 2. What does the fundamental theorem part 2 say? It says the definite integral of f of x dx is simply the antiderivative evaluated at the upper and lower endpoints and looking at that difference. Riemann sums would be a real pain in the neck and not all that practical if we had to do them all with the limit definition of the Riemann sum. Like that one question I did that took me a whole page. But the beauty is, once you got the fundamental theorem of calculus, you can do those Riemann sums just like that using the first half of calculus. All right, here's the proof of that. Okay. So consider integral from a to b of f of x dx. So this is, I think it's on page 2. The integral from a to b of f of x dx. Okay, let's let capital F of x be an antiderivative of little f. We know at least one exists. At least one exists by the fundamental theorem of calculus, part 1. Why? Yeah, well, we need f to be continuous. Yes, maybe I should have said this. I should have said that, f is continuous. But so I know there's a function g of x equal to a to x of f of t dt. What's the derivative of this function? What is the derivative of this function? Well, we could label it as g prime of x, but what is it? It's the underlying function f of x, right? So if the derivative of g is f of x, if these two are equivalent, then what's an antiderivative of f? And yeah, but we don't know what that is. An antiderivative of f would be the same thing as an antiderivative of g prime, and what is the antiderivative of g prime? G. So that is one antiderivative of f. So we know at least one antiderivative of f exists. Then so we have this other antiderivative that we've chosen. What do we know about it? What do we know about two different antiderivatives of the same function? They can only differ by a constant, right? So what do we know about f of x? Even though we don't know how it's written, we know that it's equivalent to this thing right here. Plus c. Now, I'm not saying that f of x is going to look like that, but it will be equivalent to this. It will always return the same values as this expression does. Usually, when I say think of an antiderivative of f, you will not think of this function, but this function is an antiderivative of f. But usually when you go to think of one, you don't pick this one because this one's so messy to work with. But it is an antiderivative. Okay? So here we go, we're done. Let's look at f of b minus f of a. Well, that's going to be the integral from a to b of f of t dt plus c minus the integral from A to A of f of t dt plus c. And I'm out of room. I'm going to put it down here. Put it down here. So f of b minus f of a is equal to the integral from a to b of f of t dt plus c, right? Because we said, what did we say capital F of x was? We said capital F of x, oh, golly. Where'd it go? We said capital F of x is just that function, and so if I put a b here, then I put a b here, right? Minus, what is capital F of a? It would be the integral from a to, I'm doing this one right here, it would be the integral from a to a of f of t dt plus c. What happens to those two plus c's? They cancel, which is why we've never had to worry about the plus c when we use the fundamental theorem part 2 for definite integrals. Okay. So what am I left with? Well, I'm left with the integral from a to b of f of t dt minus the integral from a to a of f of t dt. But what is the integral from a to a?
0.
It's 0. So what am I left with? The integral from a to b of f of t dt. Why was t there all along? It was a dummy variable holding the place of whom? X. What did we just show? We just showed that the difference between these two antiderivatives, evaluate the endpoints, is the net area underneath the curve. No, thank you, thank you.